So now that you've learned everything you wanted to know about heartbeat, heart anatomy, heart structure, the regulation of heartbeat, now we're going to look at some of the homeostatic consequences of cardiac cycle and how your heart and other organs in the body help balance the fluid volume in your bloodstream. So chapter 14 is more about what we refer to as hemodynamics than necessarily just about the heart, even though you can see we're starting with the heart. So one way we balance fluid movement in your blood vessels, and it's no surprise, is how much blood the heart puts out. So our cardiac output, notice this term, is how much blood is pumped by the ventricle every minute. Cardiac output is volume of blood per minute. Now contrast that with stroke volume. Stroke volume is volume of blood per beat. So if you take your stroke volume, which we said is about 80 milliliters per beat, times your cardiac rate, average around 75 beats a minute, you're going to get a cardiac output for an average individual of 5.5 liters per minute. You remember a couple of lectures ago I said 5 liters? Remember that number? What was 5 liters? How much blood you have in your body. So think about this incredible pump that is your heart. Every minute for your entire life, your heart is moving your entire volume of blood. And it never fails. If it fails, you probably don't realize it because you're done. Every minute of your entire life, your whole volume of blood is being moved by your heart. So this summary slide is where we're going with this, certainly this first portion, if not the entirety of chapter 14, because we're going to look at cardiac output, the circle with the X in it that you see in the middle. That's your heart. That's the pump. And so cardiac output is going to be influenced by the functioning of your kidney, which can be functioned by your neuroendocrine system, your central nervous system, your endocrine system. Certainly that's going to influence your diet, how much fluid you've brought in from drinking water or other fluids. But notice that cardiac output is also going to be influenced by total peripheral resistance. How contracted or dilated are all the blood vessels in your body? And so the heart's trying to pump. Your blood vessels are either making it easier or harder. That's going to result in an arterial pressure. Well, your arterial pressure is monitored by your neuroendocrine system. It's monitored by your kidneys. Your arterial pressure is also monitored by your blood vessels themselves automatically or intrinsically. And so you've got all these feedback mechanisms feeding in to blood volume, total peripheral resistance, all trying to have an impact on arterial pressure to keep it within those homeostatic levels. So that's what we're looking at in chapter 14. How does your body manage all of this integrated information, all of these biochemical mechanisms to keep us functioning in a healthy place? So cardiac output is a result of your stroke volume versus, well, not versus, but your stroke volume times your rate. So if we need to increase our cardiac output, well, we can increase the rate. And so there are chronotropic effectors, chrono meaning time. So the positive is going to be our sympathoadrenal system. Norepinephrine, epinephrine, it increases diastolic depolarization, like we saw in the previous chapter. Parasympathetic, acetylcholine, that's going to decrease diastolic depolarization or slow our heart rate. Now, when you put this into our graph, it's going to be real easy to see. Here is our normal cardiac cycle. You see our pacemaker potential in red, diastolic depolarization going up. Now tell me, looking at this slide, is this SA node or is this myocardial graph? You got a 50-50 shot, right? This is SA node. And you can distinguish that because, number one, we got pacemaker potentials, but two, myocardial cells are going to have that shoulder for the repolarization. So here's normal. If we're having a sympathetic response, do you see how that pacemaker potential, that slope is straight up? Pulls our action potentials closer together so we can have more in a certain period of time. Whereas acetylcholine is going to flatten that out. That pacemaker potential takes longer. It's going to move our cardiac cycles further apart, and it slows the heart rate. So our heart doesn't need innervation to beat, but this is going to be controlled from the cardiac control center in our medulla. That's going to signal it to either speed up or it's going to instruct it to slow down. So the rate is controlled by our central nervous system. The beat and the rhythmicity, that's controlled intrinsically by the SA node. So we can speed up. That's a way we can increase our cardiac output. Now our stroke volume, if we had more blood in the heart per beat, well, that's another way that we can increase our cardiac output. And our stroke volume is going to be largely determined in part by our end diastolic volume. After the atria inject that last 20%, what's the volume of blood we have there? Now, the amount of blood that's in the ventricles is referred to as the preload force. That's how much we have to move out of the heart. Now, the other thing that we need to consider here too is that total peripheral resistance. How constricted are those vessels we're trying to move all this blood into? Because you probably know it's easier to move materials through a big wide open tube than a little bitty teeny tiny tube. Have you done that experiment? Take a straw, a normal straw that you get at, let's say, Sonic. Put that straw into a soft drink and take a drink. You probably do this all the time, right? Now, take that same straw and put it into a milkshake. And I don't know why, but most places that serve milkshake give you the teeny tiniest straw. I usually, when I get a milkshake, I want that so bad, I almost give myself a stroke because you have to really suck on that straw because it's so small. And the fluid you're moving is so thick. So you can imagine if the heart is moving this 80 milliliters of blood, for instance, into a really, really narrow set of vessels, it's going to have to push a lot harder. Versus if it's moving it into a big, huge pipe, yeah, that's easy. So that resistance, that's considered the afterload force, and it's going to affect our stroke volume. The other thing affecting stroke volume is, well, how hard do we contract? Now, normally, remember, when we finished with our isovolumetric contraction and then ejection, get to that number 2 stage, ejection, we ejected about 2/3 or about 60% under normal conditions. But remember I said we had a built-in reserve where we could increase that number? And we can increase our cardiac output even if we stay at 60% regardless of our volume. This is kind of a neat trick that our heart's able to do. So here we have a nice graph showing cardiac output, a function of rate and stroke volume. Stroke volume is a function of that mean arterial pressure or total peripheral resistance. You can use those terms somewhat interchangeably. Our rate, negative by the parasympathetic, positive by sympathetic. But our stroke volume is end diastolic volume and contractile strength. Notice at the bottom, Frank Starling, those two names. These are two individuals that spent a lot of their research careers examining this ability of the heart to move different volumes of blood. And so Frank Starling came up with this idea, and they really measured it extremely well, that the more blood you have in the ventricle, so as your end diastolic volume increases, your contractility also increases almost at a linear scale. So they're almost directly proportional. And so this became basically the Frank Starling Law, or principle, if you will. The more blood you have, the greater the contraction. But it's typically going to equal about 60%. Until you get really, really into some strenuous exercise, then you can eject more than 60%. So as we look at our graph, here is our increase in end diastolic volume along the x-axis, our stroke volume along the y. Notice normal at rest. Do you see our almost linear direct proportional line? Now, once we get up here to our maximal activity, we plateau out because we just can't go anymore. But the reason we have this linear relationship has nothing to do with autonomic nervous system. It's got nothing to do with the vagus nerve that goes through your body. But it has everything to do with an intrinsic regulation built into the heart muscle itself. And this is the absolutely cool part about this. So think back to our cardiac muscle. How are cardiac muscle cells and skeletal muscle cells alike? They're striated. They have sarcomeric patterns. So you've got the overlapping thin actin and thick myosin. And they contract by this sliding filament action. And so recall our A bands, our I bands, H bands and M's. You remember that pattern that we have? Well, in cardiac muscle, what I want you to understand and appreciate is that the banding pattern is arranged in such a way at rest and under normal activity that not every actin thin filament can interact with a myosin molecule. That's because the actin filaments themselves overlap with each other. And in this illustration, when you look at the bottom, you can see the blue thick filaments and the thin black lines. That's our thin. Do you see how those actin filaments are overlapped? So there's a portion of actin, one of those actin filaments, that's not going to be able to form a cross bridge. It can't participate in a power stroke. So that contraction is not going to be the same distance, and it's not going to be as strong. But what's going to happen to a ventricle as you fill it with more and more blood? Think of it like this. What happens to that balloon when you fill it with more and more water, especially at Halloween? It'll eventually get to the point that it pops, but as you start adding water to it, what happens to the balloon? It expands or it stretches. So as you fill the heart with more and more blood, you stretch the muscle. And as you stretch the muscle, like you see in B and C, and finally in D at the top, that's the maximal stretch the heart can achieve. You filled it with as much blood as you can. That's where you get the maximal tensional contraction. So the more blood you have in for your end diastolic volume, the harder your heart is going to track automatically because of the overlapping of the actin thin filaments and the stretching that occurs because you put more blood in it. To me, that's just cool. I mean, you could hardly sit down and design it from scratch how the heart would function to work any better. So that's your built-in reserve. This is what we're doing right now. Overlap and active. We don't have to work that hard because we're sitting here not really doing anything that active. This is when you're running for your food or you're running away from Sasquatch or whatever. You need that reserve. And that's where you get that built-in ability. Now, this is a cardiac arrhythmia, preventricular contraction. And you may think, why in the world are we talking about that here? Why didn't we talk about that with our cardiac arrhythmias? Well, a preventricular contraction. This occurs because your ventricles contract before they should. That's the pre part. And this usually involves that ectopic sort of pacemaker activity. But when your ventricle contracts, you don't have as much end diastolic volume as you would normally do with a normal cardiac sinus rhythm. And so you force out a small volume of blood, and let's say that happens before our atrial systole. Well, now you get that additional blood coming in from the previous cycle, and here comes the next volume of blood coming in. So you have the early emptying, but in our next filling phase, you're going to have too much blood. You're going to have an increased end diastolic volume. Well, what do you experience if you have a PVC? You as an individual are going to experience this second beat because your heart's going to contract harder. You're going to feel that thump. But in this early emptying, because you have less blood, your heart's not going to contract as hard as it's been normally contracting, so it's going to feel as if your heart skips a beat. You don't really feel the extra hard one. You notice the early one because it's as if you don't have that beat. So look at our EKG. What wave do we have here? Can you see? You can't hardly see my pointer. Okay, we've got the P wave, QRST. But then do you see these crazy ones over here? Notice we've got our first QRS on the left-hand side. There's our second QRS, and then whoa. This should be about the place where we'd expect to see a P wave, but it's way too big. And since it's way too big, we suspect which chamber, atria or ventricles? Ventricles, because QRS is the big one. So that's our PVC, and notice it's not even as high as our normal QRS waves. That's our PVC. That's our early emptying, and so this next cardiac cycle, we're going to have an either stronger, harder beat because we're moving more blood. And then we get back in our sinus rhythm, and it's going to go back to its normal contractility. Every beat is regulated based on how much blood is in that particular ventricle. Now, PVCs are one of the most common arrhythmias. And if you examined young boys, 10 to 13 years old, 20% are going to have PVCs, asymptomatic. When you have PVCs that are occurring too close together, that's when you can start having some clinical situations. I remember when I was maybe about 12 or 13. I'd got home for football practice from middle school. I remember soaking in the bathtub. I was tired. You know how sometimes you lay down and you submerge your ears and you hear your heart beating? I distinctly, like it was yesterday, remember laying there and listening to my heart thump, 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 thump. And when it would stop, I was like, I don't think it's supposed to stop. And I remember, I kid you not, I remember being this 12-year-old kid laying there going, if it stops and doesn't start back, what do I do? Do I yell for mom? I remember having that conversation in my head. But that's what it feels like. It feels like that skipping of the beat. But I had no other symptoms. And then when I was in my 20s, I changed over health insurance, and they had me go do a stress test. If you ever have the opportunity to do a stress test, just say no. It sucks. Because they put you on a treadmill and they start elevating the treadmill and making it go faster and faster, and they won't let you run. You walk. Yeah, they won't let you run. And so I'm at the point they've elevated this thing and my hips are about to fly off. And they tell you, okay, when you're ready to stop, you just tell us. That's a lie. That's a lie from the pit of hell. Because I must have told them I was ready to quit for 2 minutes before I finally said, stop it now. And when they did, I couldn't walk. I'd been going long enough and fast enough that I couldn't walk. They had to carry me back to the bed. The good news through all that is my PVCs increased to a point and then they went away. And the cardiologist said that's the good kind. If it had continued and had gotten worse, that's when the PVCs are a problem. Now, here's the bad news if you have PVCs. Anxiety is a common cause. None of us have anxiety, right? Life is easy. It's a bed of roses. Well, that can be a cause, but when you look at other causes that increase adrenaline, you have other triggers like caffeine. Has anybody else got a problem with caffeine? Got to have the caffeine. I hate putting chocolate on that list because I can't believe chocolate could ever be bad. But chocolate has caffeine, any other kind of stimulants, dehydration, sleep apnea, of course, lack of sleep or exhaustion. Sleep apnea increases your resistance to adrenaline because you basically fight for your life every night when you stop breathing. So all of those things can contribute and be triggers for the PVCs. But again, as I mentioned, all those young boys, by and large, it's asymptomatic. They're not going to know anything. They're not going to experience any symptoms. And it's easy enough to reduce or eliminate the PVCs if you get rid of the triggers. So decaffeinate. By and large, I'm decaffeinated. I have about a cup of decaf a day. That's about it. And sometimes that's even too much. My sleep apnea, I got a CPAP machine, so that helps me with that anxiety. And the PVCs largely will be eliminated. Since I've been doing my healthier sort of thing, I rarely even experience them ever again. So that's the good news. So we talked about stroke volume. We can increase the contractility, we can increase the rate. Well, we can also increase the end diastolic volume by returning more blood to the heart. This is our venous return. Veins, I think we're pretty up on the fact that veins return blood to the heart. And most of our veins are filled with deoxygenated blood. But did you realize that veins actually are storage compartments for your blood? In fact, 2/3 of the volume of blood in your body at any one point in time will be found in a vein, because your veins are larger in diameter than your arteries in a generalized sense. Veins are also going to be pretty stretchy. So the stretchy nature of veins, the larger diameter veins, is going to lower the resistance of that blood to make it easier to get the blood back to the heart, because your blood pressure is much, much lower in your veins as opposed to what you find in your arteries. So here's a breakdown of where you find the blood in your body at a snapshot. 10% in your lungs, 10% in your heart. Only 10% of your systemic arteries, which is a little surprising to me. It's under higher pressure, it's moving faster, maybe that can account for that. Capillaries are small, but you have so many of them that collectively they contain about 5%. But your veins, small veins, venules, large veins, upwards of 3/4, 2/3 to 3/4 of your blood is in your veins at any one time. Now, I mentioned they're stretching, they're big because low pressure. Well, when the heart ejects the blood out into your aorta, what is our pressure of that blood that's coming out of the left ventricle? What is your textbook systolic blood pressure? 120 millimeters of mercury. That's the pressure of the blood coming out of your heart. Look at what you got left in your veins. 2. You're on the roller coaster. The left ventricle is at the top of that first big hill. You got 120 millimeters. 2 is when you're pulling into the station just about to stop. You've got no more momentum left. And so all of that blood in your veins trying to get back to the heart. And imagine being a red blood cell in your big toe. Now you've got to launch like a spaceship to go up against gravity to get back to the heart, and you've only got 2 millimeters of mercury to do that. The good news is your body is such an intricate machine, you have accessory pumps for the blood. If you were to ask somebody what pumps for the blood do you have in your heart, they would, your body, they would say the heart, and that's it. But you actually have other pumps to assist this low pressure venous blood to get back. And one of these pumps is built into your legs. And the pump is activated by doing what I'm doing right now, walking around. Because as you walk, you contract the muscles. And your veins are built into your muscles. So as your muscles contract, they squeeze the vein. As you squeeze the vein, where's the blood going to go? Any way it can, right? Path of least resistance. Well, the cool thing about your veins is they have valves that are much like your semilunar valves. They're not as tough, but they have these leaflets. And they're unidirectional valves. So as your blood moves up, either through the pumping action of the heart or through the squeezing of your muscles, there's only one direction for the blood to go, is up. And when it passes through the next set of unidirectional valves, it can't go backwards. So it's like climbing the steps or climbing a ladder. And the muscles of your legs help to do that. Breathing. As your chest expands and contracts, there's another pump squeezing those blood vessels to help squeeze and pump the blood back. So our venous return is built upon how our pumps are working, the diameter of our veins, the integrity of the valves. But we can also look at it as, okay, if we have a higher blood volume, we're going to return more blood to the heart. And as we look at where the fluid is in our body, we see that most of our fluid is going to be inside the cell. 2/3 of our body fluid's in the cell. 1/3's outside the cell. And of that 1/3 that remains outside the cell, most of it is going to be around the cells, our interstitial fluid. Interstitial meaning between the stuff, with 20% being in our blood plasma. Think back to our very first day. We had a slide of a capillary showing fluid moving in and out. You may or may not remember that slide, but here's where we're going to get into the specifics of how fluid moves in and out of our capillaries. Now, capillaries, remember, are going to be this network of vessels that are small enough that one red blood cell, single file, can move through. Capillaries are the only vessels that allow for what to happen? Do you remember that word? Exchange. Exchange of fluids, exchange of gases, exchange of nutrients, and exchange of wastes. This is an overview of what we're going to talk about in the next couple of slides. We have the arterial end of our capillary on the left, the venous end of our capillary on the right. Oxygen is going to be exchanged in the middle. But not only oxygen, fluid is going to be exchanged. And from a net perspective, a net movement perspective, on the arterial end, fluid is going to move out. And on the venous end, fluid is going to move back into the vessel. It creates almost like, you remember the hydrologic cycle in middle school? You know, the clouds condense the rain comes down, it gets into the lake, and it evaporates back up into the clouds. It's almost like that. The fluid moves out, and then it moves back in, like a cycle. And so the two driving forces that are going to determine whether blood moves in or out of a blood vessel are going to be, one, hydrostatic pressure. Inside the vessel, we refer to this as blood pressure. And osmotic pressure. This is where proteins play a huge role, and this is where a lot of the proteins, like albumin in your plasma, function as solutes to balance that osmotic pressure. So let's check hydrostatic pressure first. When we talk about hydrostatic pressure, we're going to have a pressure inside the vessel that's conferred by the volume of blood and the heart pushing it. But there's also a hydrostatic pressure outside the blood vessel in your interstitial spaces. There's not much of one, and in fact, in skeletal muscle, that hydrostatic pressure is only 1 millimeter of mercury. So when we look at blood pressure, we're going to see, okay, the pressure of your blood trying to get out, which is going to be about 37 millimeters of mercury at the arterial end, is pushing into a 1 millimeter mercury trying to get back in. So at the arterial end, we have 36 millimeters of hydrostatic pressure in an outward direction. And if that was the only pressure we had to deal with, fluid would go out. Now, when we get to the arterial end, in the tissues, there's still 1 millimeter of mercury. There's just not much out there. But notice our blood pressure is down to 17. Why do you think our blood pressure dropped so much from the beginning of the capillary to the end of the capillary? It went down 20 points, almost cut in half. Why did it drop so much? The fluid leaked out. You've got less fluid here. Less fluid, lower pressure. But notice at the venous end, we still have 16 millimeters of mercury pressure trying to push fluid back out. But remember, I said it's not just hydrostatic pressure, it's also osmotic pressure. That plays a role in this as well. And when we look at our osmotic pressure, that's largely going to be driven by those proteins that are present inside the plasma of our blood. And because of all those proteins in the plasma, we have about 25 millimeters of mercury of protein in our plasma. Now notice this is sort of different. A big number in our blood vessel for hydrostatic was trying to push out. If we have more protein in the plasma, which direction does the water want to go now? It wants to go to the protein. It wants to go to the solutes. So 25 millimeters of mercury in the blood vessel versus 2 outside, that's going to cause our oncotic pressure, which is a term we apply to protein as solute attracting water. We're going to have a much higher pressure trying to pull water back in. So let's put this all together. Now, Dr. Starling not only described that contractility in the heart, he also described these fluid dynamics in what he calls the Starling forces. So here's a little formula that he put together. If you look at the 2 factors that can force fluid to go out versus the 2 factors that can draw fluid in, and you crunch these numbers together, so fluid out, that's going to be hydrostatic pressure in the capillary trying to push out, and it's going to be the osmotic pressure of the proteins in the interstitium trying to pull fluid out, versus hydrostatic pressure in the interstitium and the osmotic pressure in the capillary. Crunch all those numbers together. There's our blood pressure, 37. You basically have no osmotic pressure trying to pull fluid out, so that's the 0. Then we've got the 1 hydrostatic pressure of our interstitium, and 25 the osmotic pressure of our plasma proteins. When you crunch those numbers together, you get a positive 11 millimeters of mercury. In this Starling equation, a positive number means fluid net movement is going to be out of the blood vessel. And as you move fluid out of a blood vessel, that is termed filtration. Circle that number. You're going to see that starting now until the rest of the semester, especially in kidney. Fluid moving out of a blood vessel is called filtration. So a positive Starling number means filtration is going to happen. So we got this 37 number because we're at the arterial end. But as filtration occurs there, when we get to the venous end, remember, we've got a lower pressure. We're down to 17 millimeters of mercury for our blood pressure. But we didn't lose that much in the way of protein. We lost fluid. And so our osmotic pressure is still around 25. And when you crunch these numbers, now we get a negative 9 millimeters of mercury. Negative numbers for Starling equations mean fluid's going to move back into the blood vessel, and that's referred to as absorption or reabsorption. So in a sense, hydrostatic pressure forces fluid out at the arterial end because that force dominates, and osmotic pressure of the plasma proteins pulls the fluid out because it dominates over the little hydrostatic pressure we still have. And this gives us a nice summary slide showing our Starling equation, showing our net filtration in the arterial end and net absorption in the venous end, a function of both hydrostatic pressure and osmotic pressure. Now, what I really want you to remember here is not the actual formula. Remember the two engines, hydrostatic and osmotic, but also remember, what does the number mean? What does a product mean? What does a positive Starling number mean? What does a negative Starling number mean? That's what I want you to remember from this, to be able to use that information, not necessarily derive it. Now, why do we spend such a large amount of time on Starling forces and fluid out, fluid in? Because clinically, you're going to see a lot of edema. You're going to see a lot of swelling. Inflammation, it's a normal immune response. But I think you can distinguish between a normal immune response and some clinical pathology like you see in this illustration. That's not normal. Here's a normal shape and size arm. We have some major event going on. And so when you look at edema, well, we might have high blood pressure, hypertension. Think about it. If you have hypertension, not only are you going to force more fluid out in the arterial end, let's say instead of having a 37, we've got a 57. Yeah, you're going to force more fluid out, right? But by the time you get to the venous end, then instead of 17, we've got 37 millimeters of mercury. That's going to be higher than the osmotic pressure, so fluid will never come back. Do you see how that could be a major problem? Now, let's think about it as well, too. Reduced oncotic pressure. How could you reduce the oncotic pressure low enough in a person with normal blood pressure so that the fluid doesn't come back? A lot of these plasma proteins are made in the liver. So if you have hepatitis, if you have cirrhosis, any kind of liver disease, so you're not making enough plasma proteins, you could end up having edema because you don't have enough albumin to function as solute to overcome the hydrostatic pressure so that fluid will come back and it just stays in your tissues. There are a lot of factors. Too much sodium. Add that sodium, that's going to be extra solute. So there are a lot of reasons why you could have clinical edema, not just in one appendage as you see here, but systemically. So that has to be controlled very carefully. Now, if you want to see the pinnacle of edema, look at someone with elephantiasis. I mean, you immediately think of the elephant man, of course. But these are conditions where you have parasitic worms that set up shop in your lymph nodes. Now, normally that fluid that remains out in your tissues, because it's all not going to come back. It's not 100%. A lot of it stays in your tissues and washes into your lymphatic capillaries that are filtered through lymphatic vessels and lymph nodes, which is really cool. Your lymph nodes not only act as filters, but all the pathogens that may be out in your interstitial tissues get washed to this location where you have a bunch of lymphocytes that can then identify them and remove them. It's not like your white blood cells have to go find them. Your body washes them to where the immune cells are, which is pretty cool. But if you block them up with parasites and the fluid has no way to get back to the circulation, it just builds up and builds up and builds up and builds up in the tissues until you end up with something like this guy. Look at his forearm and his lower legs.
How quickly does it get?
I have no idea how long it took to get this way, but you know what? You're going to see people in clinical settings, especially even in rural United States, that are going to be in dire shape before they're ever going to go to the doctor. Maybe they don't have insurance, they don't have a lot of money, or they just don't believe in doctors. In the South, you're going to see a lot, you may even see some of this in the dental settings, a lot of cancers in the mouth where the jaws are practically completely eaten away because of smokeless tobacco and everything else before they will go see a doctor. So don't look at this and go, well, that's some third world. I will never see that practice in medicine in the United States. You just never know. You can't even believe. But you know what? This is very sad, because you know what could have helped this man when it first started? Uphill. An anti-parasitic medication, remove the parasites, remove the inflammation. You would never stretch the skin so bad that it would look like this. And you'd recover and never even know that there was a problem. So this takes time. It takes a while for this to happen and to be certainly this bad.